Chemistry 3101. This is chapter 15, which deals with nuclear magnetic resonance spectroscopy. Earlier on, we looked at infrared spectroscopy. And in infrared spectroscopy, what we were trying to determine were functional groups, right? We would look at an infrared spectrum, and we could determine, whether it was a carboxylic acid or an alcohol pretty easily, or maybe a ketone or an aldehyde. And when we looked at mass spectrometry, for that we were usually trying to determine a molecular formula. So we'll put here molecular formula. And those are great. Those are very powerful spectroscopic techniques. However, an even more powerful technique is NMR, and that's going to be the subject of this chapter, nuclear magnetic resonance, and I'll explain what that name means. But what NMR gives us is the connectivity in a molecule. So for example, let's say you had propanol, so 1, 2, 3 carbons. So let's say you had one propanol, and let's say you had two propanol or isopropanol, and you wanted to elucidate the structure of one of these compounds. Well, if you were to use IR, you can see that they're both alcohols, but outside of that, there's nothing that's going to distinguish them. The fingerprint region of the two alkyl portions, the propyl and the isopropyl, would be too difficult to discern any differences there. With respect to mass spec, you might be able to determine some differences here in fragmentation, but they're both going to have the same molecular ion. However, if you were to run an NMR spectrum on one propanol versus two propanol, you would be able to tell the difference between these two compounds in probably about 2 seconds. Okay, just by looking at it, if somebody just flashed it in front of your eyes and you knew a little bit about spectroscopy, NMR spectroscopy, you would be able to tell the difference between these two compounds immediately. Very different in terms of their nuclear magnetic resonance spectrum that would be provided. So let's get into it and talk about the background of NMR spectroscopy. So NMR, which is nuclear magnetic resonance spectroscopy, is again the most powerful method that we have for determining the structure of organic compounds, because it tells us about the connectivity, or the way that the atoms are connected in a molecule. In fact, if you were to go up to any chemist who works as a chemist for a living nowadays in 2021, and were to ask her or him to do chemistry without NMR, I would say it would be virtually impossible. We can live without, or I think I could live without IR and MS. It wouldn't be an easy world to live in, but I could live in it, I suppose. I could live without TLC, but the one spectroscopic technique that, in my opinion, would be almost impossible for us to live without nowadays would be NMR spectroscopy. So you can imagine it's really important. And just like infrared spectroscopy, NMR spectroscopy is an involvement between the interaction between electromagnetic radiation, or light, not visible light, but electromagnetic radiation, and the nucleus of an atom. And what are we going to focus on? What nuclei will we focus on in organic chemistry? Well, good news is we're going to focus mainly on two nuclei, carbon and hydrogen. And the reason why is because those two atoms are basically ubiquitous in all organic compounds. So again, we're going to focus on those. And again, the crux of NMR, if you could really boil it down into its simplest form, is kind of summarized in this last bullet point, is the whole thing about connectivity, the way that a molecule is connected together. So say, for example, the difference between one propanol and two propanol, the difference in connectivity between those two molecules, there is going to affect how the electromagnetic radiation, or the light, interacts with the nucleus of each molecule. Now, if you're wondering, how does that happen exactly? Well, we're going to unfold that as we move along here. Let's talk a little bit more about nuclei. And it says here that the protons in a nucleus behave as if they're spinning. They don't spin like a top, but it is a useful analogy, and it's what we're going to use in this class. We're going to imagine, when I was a student, and I still imagine a proton as a perfect sphere, spinning around. Well, we're going to imagine that protons and neutrons, which are found in the nucleus, behave as if they're spinning. And if an atom has an odd number of protons and or an odd number of neutrons, it's going to have what's called net nuclear spin. Examples of atoms that have nuclei that have an odd number of protons and or an odd number of neutrons would be, of course, a proton. Hydrogen 1, right, because it's got one proton. That's an odd number. Carbon 13 has 6 protons, but it's got 7 neutrons. And so that has a net nuclear spin. And the same thing for nitrogen 15, fluorine 19, and phosphorus 31. We're not really going to look at the spectra of nitrogen, fluorine, and phosphorus. However, the reason that they're presented here on this slide is because they are extremely powerful and they're very useful. Again, it's not that they're beyond the scope of this class, but we have a limited amount of time in Organic Chemistry 1. And I worked in a program a number of years ago as a chemist, and I used, fluorine NMR every day. So it just depends on the kind of molecules that you're dealing with. But again, in this class, we're going to deal exclusively with protons and carbon-13. So again, going back to that spinning nucleus, well, a nucleus has a charge, and when we have a spinning charge in the nucleus, it creates a little magnetic field that we call a magnetic moment. Now, if you think about a bar magnet that you might have played with in grade school, we did this in Canada, and we didn't have a whole lot of teaching aids back in the 80s, I guess. But anyhow, if you take a bar magnet, I'm sure somebody who's hearing the sound of my voice has taken a bar magnet and put it under a sheet of paper and then put iron filings, and you can see the magnetic field around that bar magnet. Well, we can think of a similar thing happening with our nucleus, right? If our nucleus has a spin and it has a magnetic moment, the magnetic moment, again, is like a little magnetic field. So you see that overall, the field lines kind of come together in the bar magnet and they create a field going in one direction, right? And the same thing here, okay? You see them going in this direction here. Now, the top of the magnet happens to be pointing north. So again, all we're doing here is drawing a parallel between a spinning nucleus. You're like, okay, cool, yeah, movement. Okay, it's not at 0 Kelvin, so of course there's going to be movement, right? All we're doing is drawing a parallel between the spinning of the nucleus and that it creates a little tiny magnetic field. Well, you can imagine there's going to be some significance to that magnetic field. So you got all these nuclei, right? We're dealing with moles of atoms and huge numbers of atoms. Then we've got huge numbers of nuclei. And so all of these spinning nuclei create all these little magnetic fields, which are aligned randomly. Okay, normally in a sample, if you have a solution of any organic molecule, or all those little magnetic moments, they're just going to be randomly ordered. Okay, so, or what we call normally disordered, but they're just random, right? They're not in any kind of order. They're just pointing every which way. But here's where it gets interesting. If we subject those magnetic fields, those little magnetic moments, to an external magnetic field, and I'm going to refer to B0, or sometimes I call it B naught, but it's just B0. That's going to represent, that's just a variable that represents a magnetic field. Okay, everybody knows what a magnet is. Okay, if we subject those nuclei that have their own magnetic fields that we call a magnetic moment, if we subject them to a stronger external magnetic field, what happens is, just like soldiers when they're brought to attention, okay, they're going to all of a sudden they're going to align in parallel with the magnetic field. Okay, so here's my applied magnetic field from my magnet, and we're going to talk about where the source of that, or what the source of that magnetic field is, in a little bit. But we again subject those nuclei to this external applied magnetic field, and we'll talk about that in a second. And it's kind of like all those magnetic moments that were disordered, all of a sudden they align with the magnetic field, and there's two possibilities. They can either align with the magnetic field. We call that an alpha spin state, and you can see that all the ones that are labeled alpha are all pointing up, right? They're all pointing in the same direction as the magnetic field. And they can also adopt what's called a beta spin state, where they're aligned against the magnetic field. And you can see that that's going in the opposite direction. Well, you can imagine that there must be some significance to the alpha and the beta spins, what we call spin states. Okay? What's up, bud? In a couple hours. Can you? Okay. Okay. Yeah. All right. So we have the two spin states, the alpha and the beta spin state. So again, the beta spin state is opposing the magnetic field, and the alpha spin state is aligned with the magnetic field. Well, let's add a little bit more information onto that. The alpha spin state, the one that is aligned with the magnetic field, is at a lower energy, or it's what we call a lower energy spin state. And the beta spin state, the one that's aligned against the magnetic field, the applied magnetic field, or the external magnetic field, is at a higher energy. So where are we right now? We've got an alpha spin state and we've got a beta spin state, right? They are spinning in opposite directions, or sorry, their magnetic moments, I should say, are aligned in opposite directions to the applied magnetic field. And there's a difference in energy, again, between those spin states. And now what we're going to draw is a connection between the difference in energy with those two different spin states, the alpha and the beta spin states. So here's where it gets interesting. When we take an atom that has an alpha spin state, okay, it's aligned with the external magnetic field, and we expose it to electromagnetic radiation in the radio wave frequency range. So, right, you guys know the difference between, infrared and UV and visible and X-rays and gamma rays. Well, anyhow, we go to radio waves. If we expose it to radio waves with just the right energy, a photon of that electromagnetic radiation can be absorbed. And what happens is the alpha spin state is going to absorb that energy and it will flip up to a higher energy or beta spin state. Now, you guys remember the formula, the E, energy of electromagnetic radiation, is equal to Planck's constant times frequency. So the take-home message is that energy is directly proportional to frequency. And so instead of me saying, energy of the light, a lot of times I'll say the frequency of a light, okay? So again, the frequency of the radio wave that's going to be absorbed, that's going to cause this flip from the alpha spin state and beta spin state, is quantized. It has to be the exact same as this energy gap here. All right, it's going to be the exact same. Now, something else that's covered in a little more detail later on is just with respect to the difference in the energy between the alpha and beta spin states is going to be affected by the strength of the magnetic field. So I'll talk about that in a couple of slides, but let's keep moving. So what have we got so far? We've talked about the nuclei. We talked about an alpha spin state, a beta spin state. We said that there's a difference in energy between those, the beta spin state being higher in energy. And we said that we can actually cause the nucleus, or the nuclei, to flip from an alpha to a beta spin state, which is higher energy, when it absorbs a frequency of electromagnetic radiation in the radio wave range that's exactly equal to the difference in energy between those two spin states. But something we haven't talked about yet are the electrons, right? If we have a nucleus, like a proton or a carbon-13 nucleus, it's going to be surrounded by electrons, isn't it? Well, what's interesting is that the external magnetic field is also going to affect the electrons that surround the nucleus. So follow along with me here. We have our external magnetic field, B0, okay? It's going to cause the electrons to circulate, right? Once that external magnetic field is applied, it causes the electrons to start moving around, and that creates another magnetic field. So don't get this magnetic field confused with the magnetic moment of the nucleus. Now, what is the effect of the magnetic field caused by the electrons, which we call diamagnetism? You see that the magnetic field caused by the electrons, so here are the electrons circulating around the nucleus, that's what's being represented here. These field lines, okay, you notice that they're going in the opposite direction to what the magnetic moment was a few slides ago, maybe 5 or 6 slides ago. So they're going in an opposite direction. So what are they doing? They're going in this direction, so they're opposing the applied magnetic field. So the nuclei, what do they feel? If this magnetic field here that's caused by the circulating electrons opposes this one here, that means that the nucleus isn't going to feel the total effect of the external magnetic field. It's going to feel some of it, but it's going to be shielded, what we call shielded, by the effect of this magnetic field going in the opposite direction. Okay, so we say that the nuclei then experience, again, less of that externally applied magnetic field, and we say that they're shielded. And what would that mean? That would mean that they're going to take less energy to spin flip. Okay, because as I told you on the previous slide, it says the stronger the magnetic field, the greater the energy gap. Well, it stands to reason then that if the nucleus feels less of this because of the opposing magnetic field, it's going to require less energy to spin flip. It's all going to come together, and this will all have significance. So nuclei, again, that are surrounded by less electron density are said to be deshielded. So there's some important terminology that you have to be familiar with here. Shielded and deshielded. Again, let me just summarize it for you here. If a nucleus is shielded, it means that it's got electrons circulating that oppose the applied magnetic field. If it's surrounded by less electron density, then this field here is going to be weaker, and then we're going to say it's deshielded. So again, surrounded by more electrons, more shielded, less electron density surrounding the nucleus, it's deshielded. Nothing more than that. So more electrons, shielded, less electrons around the nucleus, deshielded. Okay, and if you're wondering, well, how would I have less electrons around the nucleus? Well, it's not necessarily having less number of electrons, but I would say less electron density around the nucleus, or more electron density around the nucleus, right? And electron density is something that we've talked about Avogadro's number of times this semester when we talked about electronegativity, polar bonds, electrophiles, nucleophiles. All right, well, this slide has a lot of text on it. It kind of breaks a few rules here when you're an instructor. You shouldn't put too much information on a slide, but some of this is things that we've already taken a look at. So let's see if we can really make sense of what's going on here. So again, we expose our organic molecule to radio wave energy. What does that mean? We turn the radio on next to an organic molecule and we can figure out its structure? Not exactly. We're subjecting it to radio wave energy, right, which has a certain frequency. We said that the energy is directly proportional to frequency, okay? But we have to expose it to the correct frequency in order for that alpha beta spin flip to occur, right? Because there's an energy gap between the alpha and the beta spin state, okay? And we also said that the delta E, right, the difference in energy between the alpha and beta spin state is going to depend on the electronic environment of the atom. So where does the word resonance come from in nuclear magnetic resonance? Where does that come from? Well, when the spin flips, so when the nuclei flips from an alpha to a beta spin state and it absorbs energy, again, in the radio wave range, we said that the atoms are in resonance. Okay, so when they absorb that energy, it's resonance. It's got nothing to do with resonance that we looked at in chapter 2. It's a totally different use of the word. All right. Now, you might think, and the book goes into this in more detail. He explains it, probably in more depth than I do in my slides here. But something I just want to stop on here for just a second is to think about this. Okay, you have all these hydrogen atoms in a molecule, and you subject them to electromagnetic radiation, okay, and it causes a spin flip. Well, the thing is if the electronic environment of every hydrogen atom, of every proton in a molecule was identical, then they would all absorb the same frequency of electromagnetic radiation. They'd all have the same delta E, right? They'd all have the same energy gap between the alpha and the beta spin states, and that wouldn't help us at all. Okay, there'd be no way to differentiate between the nuclei then. But the good news is this, is that since the electronic environment, the amount of electron density surrounding a nucleus has an effect on that delta E, it's going to tell us about the frequency of electromagnetic radiation that's required to cause the spin flip is going to tell us about the electronic environment of the nucleus or each nuclei. All right. A little bit more rehashing here. This is just me trying to summarize, maybe some of the things that we've gone over here. So again, we got a nucleus. It's got charge, right? A nucleus has a charge. It's got spin. It acts like a little magnet. We talked about that. We call that the magnetic moment. We apply an external magnetic field to a nucleus or a bunch of nuclei, and then we calculate or we measure the amount of energy that's required to put the nuclei into resonance. And remember, resonance means nothing more than going from the alpha spin state to the beta spin state. The good news is that instead of all the nuclei having the same delta E, since they're all in different electronic environments, or they can be in different electronic environments, I should say, whether they're shielded by electrons or deshielded, having less electron density around them, they're going to require different amounts of energy to get them to go into resonance or to cause that spin flip. And so here's what we do with an NMR spectrum, and we're going to look at a spectrum in a few minutes here. An NMR spectrum provides a signal that represents the energy necessary to bring each nucleus into resonance. Okay, so Again, since they absorb different frequencies of electromagnetic radiation, we can pretty much plot that, okay, and see how we can differentiate between nuclei. A little bit more information here about the magnetic field and the delta E, okay? Because I told you that when you take nuclei and you subject them to an external magnetic field, so let's just start with this one here. Let's say we have a magnetic field strength of 1.41 Tesla. And if you're like, that's a weird number, well, there's some significance to that, and we'll talk about that in a little bit. But let's just say you had a magnet, 1.41 Tesla. I'll just tell you, it's a very strong magnet, okay? Now, there's a certain difference in energy, right, between the alpha and the beta spin state. But as I told you earlier, the difference in energy between the alpha and the beta spin state is affected by the strength of the magnetic field. If you have an even stronger magnetic field, if you jack that up to 7.04 Tesla, again, kind of sounds like a random number, but again, I'll go into that in more detail. We have a bigger energy gap between the alpha and the beta spin state. And you might be thinking at this point, if you haven't read the book already, you might be thinking, well, who cares if the energy gap is bigger or smaller? Well, again, I know I keep saying that there's significance here, but you're going to see why, or you're going to understand why we want to have a stronger magnet, or why, maybe not, I shouldn't phrase it. Maybe I would say there's advantages to having a stronger magnet. There's advantages to having a bigger energy gap between the alpha and the beta spin states. I'll put it to you bluntly, though. The greater the magnetic field strength of your spectrometer, and we'll talk about what a spectrometer is in a little bit, the greater the magnetic field strength, to be very frank, the more expensive it is. Okay, so the higher field strength, or the higher magnetic field strength that you have, the greater the energy gap, but it also costs more money. Okay, so money doesn't grow on trees. So in order to have a higher field spectrometer, they can be very powerful and very useful. However, since they cost more money, there's only a limited number of these things to go around. All right, anyhow, how do we actually run an NMR spectrum? I know that most of you are enrolled in Chemistry 3102 at the moment, and we don't actually run our own spectra in that lab. However, if you've ever looked across the hall, you might have seen this shiny big cylinder, which kind of looks like this. It's not gray. It's not a dull dark gray. It's a shiny silver one. And then we also have one that's painted white. But we have two NMR spectrometers across the hall from the lab that you may have noticed just walking by. So where do we get these strong magnetic fields, this 1.41 Tesla or this 7.04 Tesla? How do you make a magnet that's that strong? Well, if you've ever been to a junkyard and you've seen them pick up a car using a magnet, you probably guessed that it comes from an electromagnet. So how do you create an electromagnet? I'm sure that many of you have built an electromagnet at one point in your life, where you take a wire and you run a current through it, and then you pass it around a nail, and then you can create a magnet that way. Well, it's basically the same kind of idea here, that we pass a really powerful current through a superconducting material, so something that doesn't have a whole lot of resistance to the current, and then we do it at a low temperature, okay? A really low temperature, 4 Kelvin. That's only 4 degrees away from absolute zero. And if you're wondering, where do you get that? Well, you use liquid helium in order to obtain that low temperature. And the greater current that we have, and that's why we have this high current passing through a superconducting material at low temperatures, because greater current or more current will pass through, we get a stronger magnetic field. Now, the type of spectrometers that are used nowadays, if any of you end up using an NMR spectrometer at some point in your life, we use nowadays what's called a pulsed Fourier transform spectrometer. I would just call it an FT, usually is what I call it, which just stands for Fourier transform. And if you're wondering what the heck is a Fourier transform, well, I'll mention that briefly. But the way spectrometers work nowadays is that we subject our organic molecule, our sample that we're trying to determine the structure of, we subject it to a high magnetic field. We don't vary the field strength, okay? We just subject it to the magnet, just throw it in a magnet. And then what we do is we hit the sample, or we shine. I don't like to use the word shine, because shine kind of implies that you can see it, but we subject the sample to all relevant frequencies or wavelengths of electromagnetic radiation that can be used to excite the sample. Now, what do you mean by excite the sample? I mean to get the resonance to occur, to cause the nuclei to flip from the alpha to the beta spin states. But what's interesting is that since the beta spin states are higher in energy, when the atom absorbs the correct frequency of electromagnetic radiation and obtains that higher energy spin state, it can then relax, right? It relaxes, and relaxes means it's going to go fall from a beta to an alpha. And when it does that, it's going to emit some energy, okay? And that energy is recorded. So think about it. If the difference between the alpha and the beta spin states can vary, that means that the amount of energy that's emitted is going to vary, right? And that emitted energy is recorded in what's called a free induction decay. You don't have to know anything about a free induction decay. You could Google it if you wanted to, but a free induction decay just looks like a bunch of signals that look like this on a piece of paper, okay, on a screen or on a piece of paper, and then the mathematical operation that's performed on the free induction decay, or the FID, is called the Fourier transform, which is way beyond the scope of our course. Okay, that's a complex mathematical treatment, but what it does is it enables you to see distinctly the different signals, which are a result of the resonances of the nuclei. So a little bit more information about the FID. So the FID, which is the free induction decay, has all the information of for each atom. Looks really complicated. Nowadays, in 2021, you can just literally click a button. You click your mouse like that, and it will do the Fourier transform for you immediately. And then you can see your spectrum. And we're going to look at a lot of spectra from here on out. So you can see each individual signal very clearly after that. And what we do nowadays is we take many free induction decays and we average them together. Again, I'm not going to ask you about that, but if you're interested in how spectrometry works and how we obtain an NMR spectrum, we basically pulse the sample with all the relevant frequencies of electromagnetic radiation. We do it over and over and over and over and over. You can do it. It's usually a multiple of the number 8, like 8, 16, 32, 64, 128, 256, and 1024, right? We pulse it, and the more times that you pulse it, it's like taking a picture and it getting clearer and clearer and clearer and clearer over time, okay? How do you prepare a sample, right? Everybody knows how to prepare a sample for TLC. You dissolve it in an organic solvent, and then you take a spotter and you put it on a TLC plate. Well, how do you prepare a sample for NMR spectroscopy? You just dissolve it in a liquid solution. However, the solution, if you think about it, you can't put it in a solvent like H2O or acetone, which is replete with protons, because remember that from general chemistry, what's the definition of solvent and solute? Well, the solvent is present in a greater amount. So if you were to place your organic molecule in a solvent that's full of protons and you run an NMR spectrum on it, all you're going to see is the protons that come from the solvent. So that doesn't really help you. So instead of having hydrogens, right, protons, you replace those with deuteriums, right? Deuterium is just an isotope of hydrogen. Now, you guys know the difference between hydrogen 1 and hydrogen 2. Hydrogen 2 is the same thing as deuterium. Well, you might think, well, come on, Mr. Dion, deuterium has 1 proton and 1 neutron. It's got an odd number of protons and or neutrons, right? Doesn't it have spin? How is that going to help you? Well, the reason why a deuterated solvent works is because even though deuterium does possess spin, it absorbs over such a different range of frequencies than protons do that we don't see it in our NMR spectrum, okay? So there you go. So you take the sample, you put it in what's called an NMR tube, and by a tube, it's literally a glass tube. I can do my best drawing here. Maybe I should have put a picture of an NMR tube, but it's just a long, narrow tube, and you put a cap on it to prevent the solvent from evaporating. You put the dissolved sample in the deuterated solvent in the bottom. You put it inside your magnet. You subject it to that huge magnetic field. You hit it with all the ranges of electromagnetic radiation. You get the free induction decay. You perform the Fourier transform, which is just done by a computer, and you end up with a beautiful spectrum. All right, now I was hoping to just go to this slide here, which shows you a spectrum on the bottom, but I have one more slide. Again, deuterated solvents, there are many different deuterated solvents that scientists use nowadays. This one here is what we call deuterated chloroform. You guys know what chloroform is? It's CHCl3. It's used for kidnapping. That's a joke, okay? So chloroform. So if we replace the hydrogen with a deuterium, we get CdCl3, and that's called what we call chloroform D, or deuterated chloroform. The structure is shown here. It's a really good solvent. And if you're wondering, you know, aren't there solvents that don't have any hydrogens in them? What about carbon tetrachloride, right? CCl4, that's got no hydrogens. That could also be used as an NMR solvent, no problem. What about water? Could you use water and just replace both of the hydrogens with deuteriums and have D2O? Yeah, absolutely, that would work. Again, I'm probably not going to ask you a lot about deuterated solvents, but again, you should know that the solvent that you put the sample in can't have any protons. Otherwise, it would just, you know, you wouldn't get any useful information about your organic compound. Again, here's just a picture of a spectrometer. It kind of looks like some dark, ominous spectrometer. They're usually a little bit happier than this. Anyhow, so here's your spectrometer right here. This is where the magnet is. The magnet is inside here, and there's a coil inside the magnet, and that's, which is, you know, in a jacket of liquid helium. So there's liquid helium, which is really cool. Outside of the liquid helium, there's liquid nitrogen, which is at 77 Kelvin. So this is liquid helium, then you have liquid nitrogen, and then you just have like a vacuum on the outside. And again, all that does is to keep the coil really cold so that you can generate or produce such high magnetic fields. You take your sample, so this is your NMR tube here with your sample. This is not to scale. Okay, you take the sample and you put it through the top into the magnet, and it drops into the coil like that. Again, this is ridiculous. The size of my tube is ridiculous. The tube is probably only, I don't know, 15 centimeters long or something. Here it looks like it's a couple feet. Okay. Anyhow, but you stick that in the magnet, and then you pulse it with radio frequencies using the radio frequency generator, which is shown here. And you can see there's a computer here, and on the computer, that's actually showing an FID. That's a free induction decay. And you perform the Fourier transform at the click of a button like that. So that's in essence what an NMR spectrometer looks like. And that kind of covers most of the background on NMR. Of course, like any subject in science, I mean, we could go into a lot more detail, but that gives you all the information that you need to know as to how we get a spectrum and why we obtain spectrum, what they're useful for, and where they come from. And of course, you know, you want to keep this in the back of your mind when we're looking at the spectra of organic molecules throughout the course. So here's, you know, just a run-of-the-mill organic spectrum that you could see on any day of the week. And there's a lot of information that can be gleaned or garnered from an NMR spectrum. You look at it right now and you're like, well, there's some fuzz here. It's not very useful. Well, yeah, it's really useful, and I'll go into it right now. So first of all, we can see how many signals. And the number of signals tells us the number of unique protons that there are in the molecule. So the number of signals, this would be considered a signal here, all of this would be considered a signal here, and this would be considered a signal there. So just by taking a quick peek at this spectrum, it looks to me like we've got not three protons, but three unique types of protons in the molecule. The next thing is the chemical shift of each signal. And chemical shift is measured in parts per million, and I'll explain why that is in a second. So the chemical shift down here, chemical shifts generally range from 0 to 12 parts per million. They can go outside of that. They can be below 0. They can be above 12. But generally speaking, they lie in that range. The next thing is the integration. Integration is not shown on here. So integration is, we'll put here, not shown, but integration shows you the relative number of protons in each signal. And the last thing is the multiplicity. And that is something that I don't know if we'll have time to get into today, but the multiplicity is this. You see this signal right here? Well, if we zoom in on that, how many actual peaks do you see here? I see 1, 2, 3. And so we call this, it's got a name, we call it a triplet. Okay? And that's the multiplicity of that peak. If you look at this signal right here. And when I say that, I shouldn't have said peak, I should have said signal, because there's 3 peaks in this signal, which is a triplet. If you look at this one here, it's got a total of 4 peaks in this signal. So we call this a quartet. And I bet you're waiting to see what I'm going to say about this. And you're like, Mr. Dion, that doesn't look like anything that's very pretty. Okay. Well, when it looks like this, when it kind of just looks like, you're like, I'm not sure. Maybe this, is that a triplet there? I don't know. Okay. When it looks like this, we can make it really simple. We call it a multiplet. When you're not quite sure what to do, you're thinking, or I know you aren't thinking this, but you might be tempted to say, I'll just call everything a multiplet. Everything will be a multiplet. No. But the multiplicity actually tells us, get ready for this, and think about this. It tells you how many hydrogens are next door. Okay, so just from the multiplicity, we can tell me how many hydrogens are neighboring that proton. Okay, and again, we're going to take a look at each one of these things in more detail throughout here. So let's talk about the number of signals. How many signals do we see in our NMR spectrum? Well, the number of signals that we see in the spectrum is going to depend on the number of different kinds of protons in a compound. So different kinds means unique, right? Unique types of protons. And that's what we're going to focus on for the next few minutes, is learning how to discern whether protons are unique or not. You might think, I don't know if it's unique. Maybe are these ones identical twins or what? Well, anyhow, you can use some of the knowledge that you gained in the chapter 5 in the stereochemistry chapter, that can be applied in here. But let me go over this with you. Okay, if we have protons that are identical, instead of me just calling them identical and saying these are the same, good organic chemists call them chemically equivalent. Okay, it's a little fancier, but we say that they're chemically equivalent. That just means they're the same. And if protons are chemically equivalent, they're going to produce the same signal. Same signal. Okay, and if you're still not 100%, I'm not sure what same signal is, again, you'll see more and more examples of this as we move along. But when it comes to chemically equivalent protons, we get 2 types, homotopic and an antiotopic. Both of these are chemically equivalent. They're different, right? They're different words, homotopic and antiotopic, but they're both chemically equivalent. So let's go over homotopic first. If a molecule has an axis of rotational symmetry, so the take-home message would be homotopic, and this is my opinion, the easiest way to think about it, homotopic has rotational symmetry. What's rotational symmetry? That means if you spin the molecule around, not completely, but if you rotate it some way, you get the same molecule. For example, if I was to imagine an axis here, and if I was to spin this 180 degrees, I'd end up with the exact same molecule, right? If I had this molecule, this alkene, which is isobutylene, but if I was to rotate that at 180 degrees while you had your eyes closed, and if you reopen them, you wouldn't notice any difference. The same thing with difluoromethane. If I was to have an axis here, if I rotated that 180 degrees, right, and you close your eyes and then reopen them, you wouldn't be able to discern anything. Same thing with this cyclopropane. These 2 hydrogens, if I rotate around this axis 180 degrees, you would not be able to tell any difference between the molecule. Give me a thumbs up if you just follow me on that. I know I haven't asked a lot of questions this morning, but this lecture takes a lot of, sort of content before we can get into some practice problems. Does everybody follow me? Thanks, Megan. Good. All right, great. Okay, it's not meant to be a mega complicated concept, homotopic. There we go. Now, if you're looking at a molecule that's a little more complicated than one of these molecules, let's say, and you're curious, oh boy, are these 2 protons homotopic? That's a great question I could ask on your next quiz. I could simply show you a molecule, highlight a couple of protons, and say, are they homotopic? Yes or no, right? Well, if you're really, I'm not sure if there's an axis of rotational symmetry. Let me give you an even more foolproof method. It's what's called the replacement test. All you do is you take the 2 protons in question, they're both highlighted in red over here on the far left, and you replace each of them with another atom. Now here they replace them with D, which represents deuterium. You can replace them with a chlorine. You can replace them with a, I don't care what, okay? You can replace them with a picture of your best friend. It doesn't matter. But if you replace them with another atom, each of them individually and you end up with the same compound, then they're homotopic, right? You can clearly see that these two molecules are identical. If I take this one here, and if I was to flip this 180 degrees, I end up with this molecule here. So they're identical. And so those protons are homotopic, and they're going to produce the same signal. Or again, put another way, they're going to absorb the same frequency of electromagnetic radiation. Let's move on to enantiotopic. Enantiotopic, we're not dealing with rotational symmetry here. We're dealing with reflectional symmetry. So if there's a mirror plane in your molecule, right, if you could pass a mirror plane somewhere in the molecule so that you get reflection of the two protons, that they're mirror images of one another, then you have enantiotopic protons. Now, it's not easy for me to, draw an axis or something here for enantiotopic protons. But you can imagine that if you were looking, I'll just highlight this molecule here. If you were looking at it, kind of at this angle, and what you see is you have the two protons coming up like this. You've got the fluorine coming out towards you, right? And the chlorine is right behind it, right? Let me draw it with red, okay? And I know this is kind of a goofy way of doing it, but sometimes you have to be a little unorthodox and you're explaining something to a friend, right? Well, you can see now that through here, oops, that doesn't pass through it, does it? But you can see that there's a plane of symmetry, right, running right through, bisecting those atoms, right? Remember, we can draw a line through an atom. There's no harm in that. But you can see now that there is reflectional symmetry here, and we could do the same exercise here, and he has some more pictures of that in our textbook. So these protons on each one of these molecules that are highlighted in red are enantiotopic. Now, again, they are chemically equivalent. They're going to absorb the exact same frequency of electromagnetic radiation. If you're really struggling with this, the concept of protons being enantiotopic, well, good news, you guys. You can also use the replacement test. And I'll be honest, I've taught organic chemistry for a long time. I've studied it for an even longer time. And I would say that I apply the replacement test more often when I'm dealing with enantiotopic protons than homotopic. It's just kind of just something that happens, I guess. Anyhow, replacement test works the exact same way. If you replace each one of these hydrogens individually with a deuterium and you end up with a pair of enantiomers, which you do here, you see these are non-superimposable mirror images. That's pretty obvious. At least I think it is. Then they're enantiotopic. Okay? There you go. Give me a thumbs up if you follow me on enantiotopic. And if, usually at this point, when I teach my students the replacement test, they usually think, this is a test I can wrap my head around. It's the kind of test I like. Yeah, absolutely. The replacement test is great. It's great. And don't think, oh, this is just something you learn in organic chemistry, and then once you become an expert in NMR, you'd never use it again. I would beg to differ on that. Here's a decision tree put forth by the man himself, the good man, David Klein. If you're, studying late at night and you're wondering, homotopic and enantiotopic and neither, well, what's the decision here? If there's an axis of rotational symmetry, so we'll say rotational symmetry, you've got protons that are enantiotopic. If there's a plane of reflectional symmetry, so reflectional symmetry, then you've got enantiotopic protons. And if you don't have either of those, well, then we're going to take a look at that. Then they're not chemically equivalent. And we can end up with protons that are what we call diastereotopic. All right, isn't that a store in the mall? Diastereotopic. Anyhow, so we got number of signals. So going back to the replacement test, if you try the replacement test on two protons and you end up with a pair of diastereomers, they're called diastereotopic and they're not chemically equivalent. Okay, diastereotopic protons, if they're not chemically equivalent, what does that mean? They're going to absorb different amounts of energy in order to cause resonance, to get that spin flip to occur, which means they absorb a different frequency of electromagnetic radiation. I love it when a plan comes together. Well, let's take another look at some diastereotopic protons right here. These two protons in this 2-butanol. So is this R or S 2-butanol? Let's figure it out here. It doesn't even tell us. We got group number 1. The hydrogen is in the back. This is group number 2. This is group number 3. It's going clockwise like that. So this is R 2-butanol. I don't know why Your instructor didn't put that in here, but anyhow, so we have R2-butanol. So we have a stereocenter in the molecule, and we want to know, are these two protons homotopic and antiotopic or diastereotopic? Well, if I call them, HA and HB, and if I was to replace those, okay, and I'll try to draw this quickly, but if I was to replace this one with the deuterium and then leave this hydrogen here and then try the exact same exercise, so, and I'm sure you guys are probably even faster than me on this. Probably thinking, just get on with it. I get it. But let's go over it here. So if we do the same exercise here, you can see that now you end up with two non-superimposable compounds, right? They're not mirror images and they're not superimposable. They're stereoisomers and they're not enantiomers. Therefore, these two protons are diastereotopic, right? The relationship between these two compounds is that they're diastereomers. This chiral center is identical in both of them, but this chiral center is reversed in the two of them. All right. Another way you can think about it is, sometimes I like to sit down and imagine myself being inside of a molecule. Yeah, it's totally normal. Totally normal. If you've ever done that, you're a normal person. Imagine you're standing here on this proton. Okay. What do you see? You see that this hydroxyl is on the same side of the molecule as you. So it's very clear that if you were to jump from that proton over to this proton, you are in a different environment, my friend. Now the hydroxyl is further away. It's on the opposite face of the molecule. So it's clear that these two protons are not equivalent. Again, not a lot of people like to imagine that they're dancing on molecules or jumping around inside of a molecule, but hey, it works. All right. Students love shortcuts. You know what? Students are just like everybody else, right? Everybody loves a shortcut in science, and there are some shortcuts to determining how many signals you should see, which is another way of saying, are protons equivalent? Yes or no? Do I have protons that are homotopic and antiotopic, or are they diastereotopic? Are they just not chemically equivalent? So here's some quick and dirty rules. I would recommend, if you haven't printed out the next two slides or if you haven't taken any notes, I would write down these next 4 bullet points here. First one, if you've got two protons in a methylene, a CH2, they're going to be equivalent if there's no chirality centers in the molecule, point final, okay, as we say in French. That means end of discussion. If you got two protons in a methylene and there's a chirality center in the molecule somewhere, they're not equivalent. Look, you see these two protons right here? They're chemically equivalent. Why? Because there's no chiral center anywhere in the molecule. As soon as you throw a chiral center in there, they're not chemically equivalent. Don't believe me? Let's go back here. These two protons, there's a chiral center in the molecule. They are not chemically equivalent. If we back up even more, where was I? Here, okay? There's no chiral center in this molecule. Therefore, these two protons are chemically equivalent, right? It's a CH2. There you go. Great rule, a really quick rule, or quick 2 rules, I should say. Other rules that you're going to want to apply probably hundreds of times throughout the next the coming weeks. 3 protons in a methyl group, they're always chemically equivalent to each other, right? Whenever you have a methyl group, the 3 protons are going to be chemically equivalent because you always have free rotation around this bond, right? Because a methyl group, the carbon is always sp3 hybridized, so there's free rotation. Therefore, those 3 protons are equivalent. What else? Multiple protons are equivalent if they can be interchanged either through rotation or a mirror plane. So you see in this molecule here, this is a ketone called 3-pentanone. There is an axis of rotational symmetry here. And so since all of these protons are interchangeable by that axis of symmetry, they are all chemically equivalent. And if you're wondering, well, what about these 2 methyl groups? Right? Are these chemically equivalent? Because when I rotate the molecule around that axis, and the answer is yeah, they're chemically equivalent too. All right, there we go. Another example, I'm just thinking while I'm talking to you guys, let's say you had cyclohexane. Well, what kind of protons are in cyclohexane? If we just look at the 2D structure, you have 1, 2, 3, 4, 5, 6 methylenes, right? They're all chemically equivalent, right? Because they have all these axes of symmetry. So they're all identical. Anyhow, let's talk a little more about cyclohexane. Because if you're very astute, you might have said, well, hold on, Mr. Dion. The cyclohexane isn't a two-dimensional structure. Wait a second. There's actually two different types of protons in a cyclohexane molecule, right? You guys remember the chair? The chair? Well, I've got 6 protons that are axial, right? And I've got 6 protons that are equatorial. So, I mean, come on, Mr. Dion, use your little guy here. What this guy sees is going to be different if he's on an axial proton compared to if he's like, yay, if he jumps down here, right? He's in a different environment. So those 2 protons are not equivalent, but hold the phone, they are equivalent. And if you're wondering why, if you read the book, you'll know why. But if you're wondering why, let me show you why you only get one signal for cyclohexane. Because at room temperature, we get the interconversion of the 2 chair forms, right? There's no difference between the relative energies of the 2 chair forms here. And so it's kind of like an NMR spectrometer is like a camera trying to take a picture of the molecule, and the shutter speed is slower than the interconversion between these 2 chairs. So it can't distinguish between the axial and equatorial. You get a blurry signal, if you will, and that's just an analogy. And we end up with only one type of proton like that. If you were to reduce the temperature, and this is what the title is, this slide is, variable temperature NMR. If you do change the temperature to like a minus 100, then you would be able to distinguish between the axial and equatorial protons. But generally speaking, in this class, we're only going to look at NMR spectra that are run at room temperature. All right, there we go. So let's take a look at a practice problem. So it only took us 54 minutes to get into some actual practice from our textbook. First question in the book. Okay, it takes that long to get into practice in the NMR chapter. It says for each of the following compounds, we've got 3 of them here, determine whether the 2 protons in red are homotopic, enantiotopic, or diastereotopic. So are they chemically equivalent or are they non-equivalent? So let's start with A. Who could tell me the relationship between these 2 protons? Would they be homo, enantio, or diastereotopic? Could anybody tell me about the protons in A? Yeah, they're homotopic. Thanks, Maya. The reason why they're homotopic is because there's an axis of rotational symmetry in the molecule, right? It might be a knee-jerk reaction to think, well, the methyl group's going to end up on the other side of the molecule. Well, the letters M and E are just representations put forth by human beings, okay? If you go down to the atomic level, you don't see letters. Like you don't see little H's and C's floating around in space, right? Okay, so you know that there's a sigma bond between the oxygen and the carbon, and there's a plane of symmetry there. What about these 2 protons in B? Could anybody tell me about those 2 protons? What would they be? Yeah, they'd be enantiotopic, right? The reason why they would be enantiotopic is because if you were to draw the replacement test, or to perform, I should say, the replacement test. So let's do it here. Okay. You'd end up with something that looks like this. So let's say you have 1 hydrogen here, 1 deuterium here, this deuterium here, and this hydrogen here. Well, what's the relationship between these 2 molecules? These are enantiomers, okay? These are enantiomers. And so the relationship is enantiotopic. So the first one was, I should write the answers down, shouldn't I? Homotopic. These ones are enantiotopic. And what about the last one? Well, the rule that I would use here is I have a methylene, I have a CH2, but I've got a chiral center in the molecule, and therefore these 2 must be diastereotopic. If you need to do the replacement test to prove that you would generate 2 diastereomers, then go for it. Okay? Now, the next question is kind of like, out of the frying pan into the fire a little bit, I find. In order to really get what's going on here, some students might have to take a hard look at Skill Builder. So Skill Builder 15.2 in our textbook, which covers this topic in detail. But the reason I put it here is because usually students are able to figure out at this point which protons are chemically equivalent and which ones aren't. So the question asks us, identify the number of signals expected in the proton NMR spectrum of each of the following compounds. So basically, in all three of these aromatic compounds, all we're looking for is the number of unique types of protons. Remember that when you have a methyl group, CH3, that all of those protons are equivalent. So the three protons in this methyl group are all chemically equivalent, and there's no other methyl group that's attached to an oxygen. So that's going to give you a unique signal, what's in the red circle here. I have a question for you guys. If I circle this methyl group and this methyl group, now each methyl group itself, we know for sure that they're going to give you a signal, right? One signal. But my question is, are these two methyl groups in the two blue circles, would those be chemically equivalent? Yes or no? Just would they be chemically equivalent? Do you think that they are the same? Are they in the same type of environment or a different environment? Same or different, do you think, these two methyl groups? Okay, if you're unsure, the answer is that these two groups that I have circled in blue, they are different. If I was to rotate this molecule 180 degrees, okay, I do not end up with this molecule, do I? It would end up with a molecule with an ethyl group here and this ethyl group up here. So they are not, there is no plane of reflection or rotational symmetry. There's also, and so these two methyl groups are non-identical. So those would produce unique signals. I have another question then. If I circle this methylene and this methylene, the CH2s, there are no chiral centers in the molecule. And so these two methylenes, the two CH2s, are both, they're both going to produce one signal. But my question is, are these two methylenes in the green circles, would they be the same? Would they be chemically equivalent or no? Would they produce the same signal or would they produce different signals? The ones in the green circles. Yeah, thanks, Skylar. The answer is these two are different. Okay, there's no rotational symmetry here. These are chemically different. Okay, now there are other protons in the molecule, right? I have a proton here, and I have a proton here, and I have a proton here. All three of those are going to be unique, right? There's no other proton that's in the exact same environment as this one. Same argument here and the same argument here. Now I'm just going to remove those hydrogens just because my molecules are so close together in this question. So I'll just circle here, there's a proton, here there's a proton, here there's a proton. So how many total signals do I have? 1, 2, 3, 4, 5, 6, 7, 8. I have a total of 8 signals for this molecule. Now, if I go to B, there is an axis of rotational symmetry, isn't there? Right? I have an axis right here of rotational symmetry. If I was to rotate that 180 degrees, I'd end up with the same molecule. And so this proton that I'm writing in red and this proton that I'm writing in red, those are chemically equivalent. I'll delete the hydrogens and just circle the carbons that they're on. Those are chemically equivalent. These two hydrogens are also going to be chemically equivalent based off of this rotation, right? I have another question for you. If I take the two methyl groups, there's a methyl group here and there's a methyl group here. Are those two methyl groups chemically equivalent or are they chemically different? Would those two methyl groups be the same? What do you think? There's rotational symmetry, but they're very different, right? This methyl group is attached to an oxygen. It's in a totally different environment than this one here, which is attached directly to an aromatic ring. And so how many signals would I observe in this molecule? The answer is, I would see 1, 2, 3, 4. I would see a total of 4 signals. And the last one, this molecule is called paraxylene, kind of a funny name, paraxylene. It might be helpful to draw the bonds in the aromatic ring like this. Now you can see that there's a plane of symmetry going this way and this way through the molecule. I have two axes of rotational symmetry. Therefore, these two methyl groups are identical, and all four of the hydrogens on the aromatic ring are identical. And so I only am going to see two signals for this molecule. Excuse me. All right, give me a thumbs up if that makes some sense. If you're not 100% with me, and I don't expect you to be at this point, we're just learning the subject, I would highly recommend that you take a look at Skill Builder 15.2, which goes over this in even greater detail. Okay, so what have you got to be able to do? You've got to be able to look at protons on the same carbon, and you've got to be able to say these protons are chemically equivalent because they are homotopic or they are enantiotopic. These two protons are on the same carbon. However, they are not chemically equivalent because they are diastereotopic. Then you've got to move on to Skill Builder 15.2. You've got to be able to analyze a molecule in terms of its symmetry to be able to determine how many signals or how many unique types of protons there are in each molecule. Capiche, capoche? Okay, I hope so. Well, I want to back up a second here, and maybe I should have put more slides in, but you know what? My students see enough slides through the course of a semester. So let me just back up quite a ways here. Where's my spectrum? So you see that I had this NMR spectrum, which is the first spectrum that I showed you. We've talked about how many signals. So we've gone over that part now. Now we're going to move on to chemical shift. And you see that the chemical shift is a number that is listed in ppm. And you probably remember ppm and ppb from general chemistry, parts per million and parts per billion, right? If you look at a water bottle, it'll say, you know, what minerals or what ions, I should say, are in there in parts per billion. So ppm represents parts per million. And I'm going to explain what chemical shift is, where it comes from. Okay. Again, I told you that the chemical shifts that we're going to look at in this class will range between 0 and 12 parts per million. So where do these numbers come from? What's the meaning of life? What's the meaning of chemical shift? Well, I can't help you with the first question, but I can help you with the second one. So let's move on to section 15.4, which deals with chemical shift. So you remember those deuterated solvents I told you about? Things like deuterated chloroform, CdCl3. Another good one is dimethyl sulfoxide, D6, which just represents the dimethyls. There's 6 deuteriums, one to replace each one of the hydrogens. And again, you can look in the book. There's a whole holy host. I probably have more of them in here, don't I? I don't know. Yeah, so deuterated solvents. Well, if you go to a chemical supplier and you buy a deuterated solvent, okay, you just go and you buy some deuterated solvents. You say, hey, I'm going to be running some NMR Spectra this weekend. I think I developed a blockbusting drug that's going to produce several $billion, which I am hoping to funnel into my personal coffers, you know, upon sales of this molecule. But first, before I can, get this billions of dollars for my own personal gain, I need to elucidate the structure of this molecule. So I will be buying some deuterated solvents. Well, when you buy a deuterated solvent, normally it comes doped with or with 1% TMS added to it. You might be wondering, what the heck is TMS? TMS is tetramethyl silane. And if you're wondering, what's the significance of TMS? Why would I put this junk into all of my solvents? Well, TMS has been accepted by the scientific community as a standard, an internal standard that is put in most NMR solvents, and we give it a chemical shift. We just say that it has a chemical shift of 0. It's just like sea level, right? We say that sea level is 0 meters. It's just like, if you remember in general chemistry 2, the standard hydrogen electrode, the SHE, you said it had a standard reduction potential of 0 volts. Well, it's the same thing. TMS has a chemical shift of 0 parts per million. And so we measure chemical shifts relative to the chemical shift of TMS. So chemical shift, which we define as the variable delta, which is a lowercase d in the Greek alphabet. So chemical shift is equal to the observed shift from the tetramethylsilane in hertz. Remember, hertz is a unit of frequency, right? E is equal to h nu, and nu is equal to seconds to the -1, or hertz, kind of a, Gen Chem 1, Gen Chem 2 review here. Anyhow, so you take the frequency of the absorbance of the electromagnetic radiation with respect to TMS, and then you divide it by the operating frequency of the instrument. And if you're wondering, what is an operating frequency of an instrument? Well, remember that magnetic field, B0, for our big old magnet? Well, the magnetic field is directly proportional to frequency of, or directly proportional to the frequency of the magnetic field, I should say. So the strength of the magnetic field is directly proportional to the frequency. And so we have an operating frequency of our NMR spectrometer. And the frequency is also directly related to, again, the magnetic field. It's also directly related to the energy. So what's the significance? Remember, I told you that the higher the magnetic field, the more expensive it was. So to put it another way, the higher the operating frequency of the instrument, the more expensive it is. And again, I'm going to explain to you what the significance is, why you would need a more expensive spectrometer. But here's the idea, or here's how we calculate a chemical shift. So again, we measure the frequency of the electromagnetic radiation required to cause that spin flip for the proton with respect to trimethylsilane, which we assign a value of 0. Okay, so say, for example, you are running benzene. Benzene is C6H6. It's got one type of proton, right? All 6 of these protons going around the molecule. If you need me to draw them in, I'll do it. But all 6 of these protons are chemically equivalent because of more than one axis of rotational symmetry. So we've got one type of proton. They all absorb this frequency of electromagnetic radiation. You divide that by the operating frequency of the spectrometer, which is, let's say you have a 300 megahertz instrument, and that is a very common frequency, operating frequency for a spectrometer. We take the chemical shift from TMS, and I'm kind of re-explaining this too much, but you divide it by the operating frequency, and you end up with this number, which is 7.7 times 10 to the -6, right? A million is 10 to the 6. So we express 10 to the -6 as parts per million. It's just expressed another way. Now, what if you had a cheaper instrument? What if you only had an instrument that had an operating frequency of 60 megahertz? You could actually probably buy a 60 megahertz spectrometer, used one, on eBay for not very much. And you could really, if you really wanted to, I suppose you could set it up in your garage. Well, if you had this cheaper spectrometer, the observed shift from TMS of your benzene protons only occurs at 436 hertz. So then it would be a real pain in the butt if everybody had a different spectrometer and all you did was report your chemical shifts in hertz. Then everybody would get different numbers. That would be very annoying. This university has a 300, megahertz spectrometer. That university has a 500 megahertz spectrometer. There's some scientists up in Boulder that have a 250, so then you're all going to get different frequencies. So what you do or what the scientific community has done to avoid that kind of catastrophe is we divide again by the operating frequency of our spectrometer, and look what we get, the same number that we got on the last page, right? So you always end up with the same chemical shift, okay? Again, which you express as parts per million, right? Parts per million is just a dimensionless number because hertz cancel out like that. And again, most proton NMR signals that we're going to see in this class are going to be between 0 to 12 ppm. Here it says 0 to 10. I need to fix that because we're going to see all kinds of signals that will come out higher than 10 parts per million. So that's where chemical shift comes from. I know we've only got 3 minutes left. I just want to mention something here very quickly to you, which is that there is an older type of NMR spectrometer. Not because remember this morning I taught you about the FTIR, the Fourier transform. which is something that's performed on the FID, which is the free induction decay. Okay, well, the first NMR spectrometers, instead of pulsing the sample with all frequencies of electromagnetic radiation, what they did is they held the frequency of electromagnetic radiation constant, and they varied the field strength of the magnet. Okay, and so the signals that come out, at the far end of the spectrum, we call those downfield signals, and then the signals that are closer to 0 parts per million, we call those upfield. The only thing that you guys really need to know from this slide, in my opinion, and I'm the guy who makes up your quizzes, is downfield and upfield. So if I'm talking about downfield, I'm talking about this direction. And if I'm talking about upfield, I'm talking about this direction. Okay, so if I say further downfield, I'm going to the left on the spectrum. If I'm saying further upfield, I'm talking about moving to the right on the spectrum. All right, there we go. So why don't we stop there? In next class, we're going to talk more about chemical shift, and I'm going to talk to you about the relationship between magnetic field and resonating frequency, upfield, downfield, higher energy, lower energy. And then what we really want to get into next class is splitting, okay? So I'm going to show you what we're going to take a look at very quickly. We're going to talk more about chemical shift. We got a ways to go on that. Then after chemical shift, and you can see chemical shift is pretty long, we're going to talk about integration. That's a much quicker concept. I don't want to use the word simple, but a quicker concept. And then if you want to do yourself a favor before next class, I encourage you to read the section on multiplicity, because if there's one section that's going to be important for you guys who are in Organic Chemistry 1, the most important section in this book would probably be the section on multiplicity. I'm not taking away from any of the other sections, but you have to understand multiplicity in order to master the content in this chapter.